All right, we just got done doing chapter 5, which was all about the different techniques of factoring polynomials. So we worked with a single polynomial at a time, and we talked about all the different techniques of factoring and solving by factoring, and that's going to be really important when we start this chapter, chapter 6. Because in chapter 6, we're going to talk about having multiple polynomials written as a division. They're called rational expressions. So a rational expression is any expression that can be written as a quotient, that's a division, of two polynomials. For example, 7 over 3 is technically a rational expression, two polynomials written as a division. 5 over x plus 6, or even a t squared minus 5t plus 6 over 4t squared minus 7. I have two polynomials written as a division problem. It's called a rational expression. Now, before we get into adding, subtracting, multiplying, even dividing these rational expressions, we've got to consider what we call domain restrictions. Because we have a fraction now and we have a denominator, hopefully we know by now that in math we're not allowed to divide by 0. It's undefined. So we have to be careful to avoid certain values. For example, if I had this rational expression, x plus 5 over x minus 7, x can be lots of things in this expression. However, it can't be anything that's going to cause this denominator to equal 0, because we can't divide by 0. And so if we take that x minus 7, and we have to figure out what it can't equal in order to be 0, I can make a little equation and solve by adding 7 to both sides, and I end up getting x can't equal 7. X can be anything else except for positive 7, because plugging in a positive 7 would cause a 0 in that denominator. So we have to be careful of those domain restrictions. Let's do an example. Example number 1 says, find all the numbers for which the rational expression is undefined. So remember, when we have a rational expression, we have a denominator, and that denominator can never, ever, 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 ever equal 0. So let's set it equal to 0 and figure out what x can't be. So when I take that denominator, my x squared minus 3x minus 10, and set it equal to 0, this kind of looks like last chapter, where we can solve by factoring. We already have everything to the same side. It's in order. Make sure you look for a GCF, and then make sure you continue following your steps for factoring. This one looks like a basic factor problem. So what numbers multiply to negative 10 that add to negative 3? I got negative 5 and positive 2. Now let's keep going and figure out what x is. So when I set it equal to 0, I ended up getting x equals 5 and x equals negative 2. But what this actually means is x can't equal 5 and x can't equal negative 2. X can be anything else, but if x equals 5 and you tried to substitute in a 5, you're going to get a 0 in your denominator. If x equals negative 2 and you tried to plug it in, you're going to also get a 0 in your denominator, which we know we can't have. So x can be anything else except for 5 and negative 2. Those are our domain restrictions. Let's do another one. If I have this polynomial, I've got to be careful where my denominator equals 0. So let's take that denominator, let's set it equal to 0. I actually factored both the top, the numerator, and the denominator on this one. If you look at the denominator, whatever causes it to equal 0, if I set each of those factors equal to 0, I ended up getting x equals positive 5 and x equals negative 5. But actually, we should probably say that x can't equal 5 and x can't equal negative 5, because those are my domain restrictions. X can be anything else except for positive 5 or negative 5, because then that would cause a 0 in my denominator. So make sure you always, always, always look for those domain restrictions. It's going to be important later on, because we can never divide by 0.